What's up? So, all right, guys, let's continue this equilibrium forever. Le Chatelier's principle. All right. Le Chatelier's principle to me is very, oh, still I'm sniffing. Look at my nose, it's so red. I like Le Chatelier's principle. Some students struggle with it, I'm not sure why. I'm going to share my screen. I may or may not reference some questions in the document that I put down there in your Google Classroom. Depends on how I feel this goes. All right. Now, I am going to start by writing a couple of things. And I do have a couple practice problems. Oh, I got to share my screen here too, don't I? Come on. Sometimes it's easy, sometimes it's hard. Oh, poor little nose. I should have brought some more expensive tissues. I don't know what's going on. I don't usually have problems like this. Okay, guys. So let me get this out of my way. And let me just talk to y'all for a minute. Le Chatelier's principle. What does it state? It says that when a system that is at equilibrium, okay, this is so logical, is interrupted, right? When you mess up the equilibrium by putting a stress, is the word they use, on the system, then what does the system do? It reacts in a way that allows it to reestablish equilibrium. That's Le Chatelier's principle. When you put a stress on a system that is at equilibrium, the system will shift in a manner that will undo that stress and take it back to equilibrium. It will reestablish equilibrium. What kind of stresses do we have? Well, we've got concentration changes. And we've actually already talked about this. I just never used the word Le Chatelier with you. But when you call concentration changes, right, the rate of the forward no longer equals the rate of the reverse. Right? So we're no longer at equilibrium. And we now have a Q system. Remember, because Q essentially is K when you're not at equilibrium. And if Q is greater than K, then we will shift to the left to reestablish equilibrium. Right? And if Q is less than K, then we will shift to the right to reestablish equilibrium. I forgot to put the left there. Shift to right to reestablish equilibrium. Okay. Let's take a moment to look at your notes. Unit 7 notes. Oh, I was scrolling through to see what's up ahead of me. What am I going to have to get into? Le Chatelier. Let me wait. Look at that. Le Chatelier's principle. This is in your notes. All right. So they're talking about us doing a change, a stress, and the equilibrium will have to shift in order to bring Q back into numerical agreement with K. So let's look at some concentration changes here. Concentration. All right, we'll deal with the others later. So here's my equilibrium system. It has a negative delta H. It tells me that heat is a product. That is not going to be a factor right now because we're nearly discussing concentrations. So if I increase the concentration of nitrogen and hydrogen, right? So what did I do? I'm going to write in a different color. I need you to understand this, and I think you will, but you need to be able to explain it. I've got more nitrogen and hydrogen, right? My brain is going, okay, I have more reactants. Okay, okay. Forward reaction is going to increase, right? Rate increases. Therefore, in order to reestablish equilibrium, I will see more products formed at the expense of my reactants. Even though I added reactants, so that makes it hard, so I may just say more products formed. All right. And you see we have a shift to right-hand side. This looks like a typo. Less nitrogen and hydrogen on right-hand side. Oh my goodness, y'all, that's looks like a typo, doesn't it? Tell me if I'm wrong. Let's look at this again for the next one. I know I'm making this sound harder than it is. That's because you have to be able to explain it harder than it is. If we increase the concentration of ammonia, right, we increase the concentration of a product. There are more product molecules to react. This will cause an increase in the reverse reaction rate, right? Because we increased the concentration of product, Q will now be greater than K, right? Originally up here, Q would have been less than K, if you think about it, because it's products over reactants. I know I'm making this too hard, but you need to be able to answer. You need to understand Q in relation to K and be able to explain it when you're doing a Le Chatelier problem. So Q will be greater than K, and we will shift left to reestablish equilibrium. All right, and so what we will see is an increase in reactant particles. All right, now, not all stresses, right, let's do this one more time. We increase the concentration of hydrogen and iodine. Here is our reaction. If these concentrations go up, then our forward rate is greater. Our Q would be in what relationship to K? It would be less than K because my P over R, my R has gone up. And I will shift to the right to reestablish equilibrium. I hope this isn't too messy for your notes. I'm feeling like it is right now. I'm feeling like it is. I'm feeling like I should stop and redo this. Okay, I won't do any more on this screen. How about that? Let's get a different color, and we will increase the concentration of hydrogen iodide, right? So here we are increasing the concentration of the product. So in terms of Q and K, right? Think about it like this. P is over R. If this goes up, what does Q do? Q goes up. So Q is greater than K. We will have to, hold on. What do we do? We added products. So the reverse rate increases. We will see a net increase of reactants. And that is a shift towards the left in order to reestablish equilibrium. Right? I say all these things because who knows what the question exactly is going to ask. I have noticed quite a liking of AP, the College Board to, they are very fond of this comparing Q to K right now in terms of Le Chatelier. So if you can manage that, that's cool. All right, as I told you, I won't reflect that anymore. I might use my negative delta H here and my positive delta H there. So let's go back to our notes. Oh, that's not our notes. These are our notes. Okay. So we just talked about concentration changes, all right? What other changes might we have? We could have, we could add, decrease concentrations. We could have pressure changes. The concentration changes are the easy one. Pressure changes are pretty easy too, all right? Now, when the pressure is changing, you need to focus on the number of moles of gas particles only, both reactants and products, but you're only concerned with gases because gases are all that we are affected by our pressure here, right? For the most part, solids and liquids are not. So we will go into gas plus 3H2 gas yields 2NH3 gas. And we saw that this was a negative delta H. That's from that practice problem we just looked at. So let's say that the volume is decreased by 2, right? We now know, or the volume is decreased, right? If the, I'm not even going to say by 2, the volume is increased. Well, this causes the pressure to increase. Okay? So we had a system that was chilling out at equilibrium. The partial pressures were not changing. We squeezed the system together, its volume. We pushed it together. We changed the container, right? Or we increased the pressure, thus decreasing the volume. It wasn't rigid. I don't know. We caused their chilling out at equilibrium. We increased the pressure. So what is the system going to do to reestablish equilibrium? The system needs to cause the pressure to go back down. Okay? Oh my gosh, hair's all over me. I'm not throwing those on the floor. The system needs to cause, therefore, system must shift in the direction that causes the pressure to go down. Will decrease the pressure. Well, okay. Well, which side is going to have the lower pressure? Over here, I have 4 moles of a gas. Over here, I have 2 moles of a gas. This is more gas. This is my higher pressure side. This is my less gas. This is my lesser pressure side. So if we had this system at equilibrium, chilling out, and you did one of 2 things. You decreased the volume or you increased the pressure. One will cause the other. Then the system needs to cause that pressure to go back down. So in this scenario, that will be a shift towards the right. Products, right? And we will see, in fact, an increase in the number of products and a decrease in the number of gaseous reactants. Recall that this is all in the same system. I've had students get confused with that before, right? It's all in there. It's not going anywhere. Okay, so if I were to look at our other system that we had down there, okay, and notice that these are all gases. And I want you to notice this, it's very important. There are 2 moles of a gas here, and there are 2 moles of a gas here. In this scenario, changing the temp pressure, or volume is what I meant, will not affect the equilibrium position. Okay. All right. Because any change that happens to one happens to all, and there will be no overall net change of ratios, or you won't need to reestablish. So there will be no shift. Okay. The other thing is that adding an inert gas, right? An inert gas that is an unreactive gas, such as a noble gas, to an equilibrium system that contains other gases will have no effect. It does not react. It is not a part of the equilibrium expression. It will not affect the forward rate or the reverse rate. Okay? So it won't affect the concentrations of anything. So it won't affect the forward or the reverse rate. Adding an inert gas has no effect on equilibrium positions. Okay? Okay, so that's it with gas or pressure and volume. The last thing we need to discuss is temp. Okay, now this is the only stress. Remember, they call these things stress. This is the only stress that affects K, right? If I change concentrations, we just have to reestablish equilibrium so we get back to K. If I change pressures, we just have to reestablish equilibrium so we get back to K. If I change temperatures, I changed K. We got to get a whole new system, okay? Whole new ratio of products to reactants, typically increasing the temperature sends the reaction to the forward side. Not always. Let's look at what's going on. You must notice, you must take note of whether reaction is endothermic or exothermic, right? Or some data may allow us to determine if it's endothermic or exothermic by looking at what happens to the temperature and what happens to the concentration. Right, this will be the last thing with Le Chatelier. Le Chatelier shows up a lot, guys, so you can't overlook this. All right, so N2 plus 3H2 yields 2NH3, all are gases, and this is a negative delta H. So this is an exothermic, and I immediately see heat as a product. All right, so I can literally, I'm going to put a circle around this and move it over. Once I see that this is exothermic, I would literally either write the word heat down as a product because it comes out, or I see it, right? So now let's increase the temperature of this system, right? Well, essentially, I am adding the heat to the reaction. Well, the heat is a byproduct. So if I add the heat, the system's going to go, I don't want that heat. I'm going to go over there and get rid of it. So I'm going to shift over here to where there is no heat to minimize the effects of that addition of heat, right? I already give off heat. And if you're going to make it even hotter, I'm going to go over here where there is no heat. We don't give off heat when we're over here, all right? So I will, in this situation, right, if it is exo and I increase the temp, I don't memorize this stuff, just make sense of it. If it's exo and you increase the temp, we will see an overall shift towards reactants. Okay. And we will also see a change in our K value. So if we shift towards the reactants, and K or Q is equal to products over reactants, then we're going to see this value increase and we're going to see our K value decrease. So in this scenario, we will have a decrease in our constant. All right. Now, if, you know, an opposite to that, we were to decrease the temp, right? Let me change that color. Then you would want to see it in a way to where, sorry, I'm just trying to find a different color, right? If we decrease the temp, right? Then that would be like looking at this equation right here. Instead of adding the heat, I took the heat away. Well, if I take the heat away, the system is going to go, we need to get that heat back. All right. We need to get that heat back. So let's proceed in the forward direction to get more of that heat back. So we would see if it's exothermic and we decrease the temp, we would shift right. We would increase the concentration of our products and the value of K would increase. The value K would go up. All right. Once again, I don't memorize that. Just make sense of it. It's so easy to make sense of. Last one, H2 plus I2 yields 2HI, positive delta H. Therefore, you want to see heat as a reactant, okay? And then just apply the same logic. If we add heat, the system's going to come over to the other side where there is no heat. We will shift right. That was an endothermic reaction, and the temp went up. Once again, don't memorize that. It's easy. It's too easy to figure it out to worry about memorizing it. If and the what would happen to K if I shift right? I get more products than reactants, so K would also go up, right? Now, last scenario, I decrease, it's endothermic, positive delta H, decrease temp, right? That means I'm essentially removing the heat. The system says, hold on, wait a minute, I want my heat back. I'm going to shift in the direction where that heat is. So I will see a shift left. I will have more reactants at the expense of my products, right? Less products. And I will also see that the value of my K will go down, K decreases. Boom. Getting there, guys, we're getting there. Okay, I'm gonna stop and I'll talk to you later. Bye. Sun's starting to go down.